are going to introduce the concept of conditional probability. So, sometimes after conducting a random experiment or after observing certain random experiment, we have some partial information about the outcome of the experiment. Now, in the light of that partial information about the random experiment or about the outcome, if we want to find out the probability of certain event, then the probability gets modified. Let us take a very simple example. Suppose we say a die is rolled, suppose it is a fair die, and let us say B is the event that an even number occurs, and if I say E is the event that the number 2 occurs. Now, if I want to find out probability of E, it is equal to 1 by 6. However, if I know that an even number has occurred, then probability of E given that B has occurred is 1 by 3, because the B has elements 2, 4 and 6. That means, my sample space has been restricted to consist of 3 elements 2, 4 and 6. Now, out of this, if we say 2 occurs, then it is one of the 3 possibilities, and therefore, the probability of that is equal to 1 by 3. So, you can see that the effect of the partial information makes us to make helps us in making better probability statements. So, let us define formally the conditional probability. So, if I say that omega B P be a probability space and let B be an event with positive probability, then for any event A, the conditional probability of A given that B has already occurred is defined by probability of A given B. So, this is the notation, probability of A given B, that is defined as probability of A intersection B divided by probability of B. So, now given any event B, if we are defining the probability of A, then first of all we should check whether it is a proper probability function satisfying the axioms of the probability. Let us check that. So, we state it as a result that P dot B is a valid probability function. Meaning thereby that it will satisfy the 3 axioms, that is probability of A given B, that is equal to probability of A intersection B divided by probability of B. Now, according to the assumptions of the probability, probability of A intersection B is always greater than or equal to 0, probability of B is strictly positive. Therefore, this is always greater than or equal to 0 for all events B. So, the first axiom is satisfied. Let us look at the second axiom, probability of omega given B. This is equal to probability of omega intersection B divided by probability of B. Now, note that B is a subset of omega, therefore, the numerator will be probability of B divided by probability of B, and therefore, it is equal to 1. The third axiom is the countable additivity axiom. So, let us consider A I be a disjoint sequence of events. Let us consider probability of union A I given B. Now, by the definition of the conditional probability, this will be equal to probability of union A I intersection B divided by probability of B. Now, in the numerator I can apply the distributive property of the unions and intersection. So, this becomes probability of union of A I intersection B divided by probability of B. Now, here note that A I's were disjoint, basically we can consider them to be pairwise disjoint. So, if they are disjoint, then A I intersection B's will also be pairwise disjoint, and therefore, by the axioms of the probability, by the third axiom, I will have probability of union A I intersection B is equal to sigma I is equal to 1 to infinity probability of A I intersection B divided by probability of B, where each of the term then becomes probability of A I given B. So, you can note here that probability of the union is equal to sum of the probabilities, which is the countable additivity axiom. Therefore, the conditional probability function is a well defined probability function. Now, let us look at some direct consequences of this definition of the conditional probability. Let us consider, say, the statement probability of A given B is equal to probability of A intersection B divided by probability of B. Now, this statement we can write as probability of A intersection B is equal to probability of B into probability of A given B. So, an interpretation of this statement is that the probability of simultaneous occurrence of A and B is equal to the conditional probability of A given B multiplied by the probability of B alone happening. If we interchange the roles of A and B, then we can also write it as probability of A into probability of B given A, of course, provided we consider that probability of A is positive. Now, this representation of giving the expression for the simultaneous occurrence probability in terms of a product, where in the product one term is a conditional probability and another term is a marginal probability, is known as multiplication rule. So, this is called multiplication rule. So, the general multiplication rule is let us consider events A1, A2, AN be events with now, in order to define the conditional probabilities, the probabilities must be positive. So, we can take the smallest event which may occur in the definition, and we can consider the probability of that to be positive, and then the probability of intersection A I is equal to 1 to n can be expressed as probability of A1 into probability of A2 given A1 into probability of A3 given A1 intersection A2 and so on, probability of AN given intersection AI I is equal to 1 to n minus 1. Let me give this statement number 1. So, in order to prove this one, we can follow induction. So, by induction, if we want to see for n is equal to 1, the statement will reduce to simply probability of A 1 is equal to probability of A 1, which is trivially true. So, for n is equal to 1, the statement is true. For n is equal to 2, it is true, as we mentioned by the definition of the conditional probability, that probability of A 1 intersection A 2 will become equal to probability of A 1 into probability of A 2 given A 1. Now, the statement for n is equal to 2 will be used for extending from k to k plus 1. So, let 1 be true for n is equal to k, and consider for n is equal to k plus 1. So, probability of intersection I is equal to 1 to k plus 1. Now, this one we can express as probability of A 1 intersection A 2 intersection A j, say j is equal to 3 to k plus 1. So, here if you see in the intersection, these are k minus 1 sets and this is 1 set. So, this is total k sets, and we have made the assumption that the statement is true for k. Therefore, we can write it as probability of A 1 intersection A 2 into probability of A 3 given A 1 intersection A 2 into probability of A 4 given A 1 intersection A 2 intersection A 3, and so on up to probability A k plus 1 given intersection A j is equal to 1 to k. And now, the first statement we can express as probability of A 1 into probability of A 2 given A 1, and all the remaining terms will be there. Hence, the statement 1 is true for n is equal to k plus 1 also, and therefore, by the principle of mathematical induction, the general multiplication rule is true. The significance of this result lies in that many times we are not aware of the probability of the simultaneous occurrence. It may be somewhat difficult, because what may happen that the events are conditional, that is after occurrence of one something may happen. For example, if a person is sick with a certain disease and he takes a treatment, what is the probability that he will be cured? Now, the probability of simultaneous occurrence of this event may not be so simple. However, if we know that the percentage of people who get cured by taking that particular treatment and how many persons eventually get recovered, then this probability can be calculated. That means, if I say A is the probability of getting cured, B is suppose A is the event of getting cured and B is the event of taking a particular treatment. Now, if we look at the percentage of people actually getting cured and the percentage of people who take the treatments and they are cured, or in the reverse way, if we look at the percentage of people who take the treatment and the out of the percentage of the people who take the treatment, how many get cured, then this probability can be evaluated. Let me write it as a example. Let A be the event person gets cured, B is person takes a treatment. So, now if I look at, suppose probability of A intersection B is to be determined, then we can write it as probability of B into probability of A given B. Suppose we know that how many people take that particular treatment, suppose 90% of the people take the treatment, and of the number of people who take the treatment, suppose 80% get recovered, then this probability turns out to be 0.72. which might have been difficult otherwise. And now, this representation that a certain event can be considered as a consequence of certain other event or happening after a certain event. This leads to some interesting possibilities, and one of the major things is the so called theorem of total probability. So, let B 1, B 2 etcetera be pairwise disjoint, that means mutually exclusive events with B is equal to say union B I is equal to 1 to infinity. Here it could be a finite union also, it will not make any difference to the actual statement of the theorem. Then for any event A, probability of A intersection B can be decomposed as probability of A given B j into probability of B j, j is equal to 1 to infinity. Further, if probability of B is equal to 1 or say B is equal to omega, then probability of A is equal to sigma probability of A given B j into probability of B j. So, you can see here, if we treat the event A as a consequence of either of B 1, B 2 etcetera, then the eventual probability that A occurs can be represented in terms of that it has been caused by B 1, it has been caused by B 2 etcetera, and the corresponding probability of those causes themselves. We will look at some example here, and but firstly let me give the proof of this. So, consider A intersection B. Now, A intersection B can be written as A intersection, and the representation for B is union of B j, j is equal to 1 to infinity. By applying the distributive property of the unions and intersections, we can write it as union of A intersection B j, j is equal to 1 to infinity. Now, we notice here that B j's were pairwise disjoint sets. Therefore, A intersection B j's will also be pairwise disjoint, and therefore, the countable additivity axiom of the probability applies here, and you can write probability of A intersection B as summation of the probabilities of A intersection B j. Now, by applying the multiplication rule on this simultaneous probability, this becomes probability of A given B j into probability of B j, which is actually the statement of the theorem of total probability. Now, we look at if probability of B is 1 or B is omega case also here. So, if probability of, if we take probability of B is equal to 1 or probability of B complement is equal to 0, then probability of A intersection B complement is 0, and therefore, probability of A can be written as probability of A intersection B plus probability of A intersection B complement as probability of A intersection B, and so the statement follows. Similarly, if we are saying that B is omega, then A intersection B is simply A, and the statement is true. So, let me give an example here. Suppose a calculator manufacturer purchases his ICs from suppliers say B1, B2, B3 with 40% from B1, say 30% from B2 and 30% from B3. Suppose 1% of supply from B1 is defective, 5% from B2 and 10% from B3 is defective. What is the probability that a randomly selected IC from the manufacturer say stock is defective? Now, here if we consider the event say A, that the IC is defective, then probability of A can be represented as sigma probability of A given B j into probability of B j, j is equal to 1, 2, 3. That means, since the IC could have come from either first manufacturer or from second manufacturer, second supplier or from the third supplier, and therefore, the consequence that it is defective is also the probability is dependent upon who supplied that. So, this becomes probability of A given B 1 into probability of B 1 plus probability of A given B 2 into probability of B 2 plus probability of A given B 3 into probability of B 3. So, now probability that it is defective given that it came from the first one is only 0.01 and the probability that it was supplied by the first supplier is 0.4. The probability of being defective from the second supplier is 0.05 and the probability that supplier 2 supplied it is 0.3. Probability that it is defective provided it was supplied from the supplier 3 is 0.1 and the probability of getting the supply from the third supplier is 0.3. So, eventually this turns out to be 0.004 plus 0.015 plus 0.03, which is equal to so the eventual probability of the IC to be defective is approximately 0.05. Although individually if we see from the first supplier only 1%, from second supplier 5% and from the third supplier it is 10%. But since the procurement is mixed with the different percentages getting supplied from different suppliers, therefore, the actual probability turns out to be 0.049. A further you can say consequence of this cause effect relationship is that sometimes we are knowing the final outcome. Now, what is the probability that this outcome was caused by something? Now, this representation, or you can say this way of looking at the probability is called posterior probability, because here we can consider the events B 1, B 2, B 3 that the supplies came from first supplier, second supplier or third supplier as prior events or something which is happening before. Now, being defective or not defective is an event which is occurring after that, because it is after procurement. Now, suppose it says that, suppose we take suppose the IC is supplied and somebody takes it and it is found to be defective. Then what is the probability that it came from first supplier, or it came from the second supplier, or it came from the third supplier? This way of looking at this probability is called posterior events, or the probabilities of the posterior events. So, the result for this is called Bayes theorem. Let me state the result first. Suppose B 1, B 2 etcetera are pairwise disjoint events with union of B j is equal to say omega. That means, they are exhaustive also, and we are given a priori probabilities, probability of B I as positive. Then for any event A, of course, since conditional probabilities are involved, we must say probability of A is positive. Then we define probability of B I given A, that is equal to probability of A given B I into probability of B I divided by sigma probability of A given B j into probability of B j. J is equal to 1 to infinity. So, let us look at the representation of this. This means that we know the final outcome A. What is the probability that it was caused by the ith cause? So, this is the posterior probability, and this Bayes theorem actually helps us to calculate this. It is calculated in terms of the prior probabilities and the consequent probabilities, which are called like the cause effect relationship, that what is the probability that the event was caused by the ith cause. So, the eventual posterior probability can be represented in terms of this. This reverse relationship, it is due to Bayes, Reverend Thomas Bayes, and it was published in his treatise published in 1763 posthumously. The proof of this statement is let us look at the proof of this. So, we will just apply the definition of the conditional probability. Probability of B I given A is equal to probability of B I intersection A divided by probability of A, by the definition of the conditional probability. Now, what we can do is that in the numerator we can apply the multiplication rule in the reverse way. So, this becomes probability of A given B I divided into probability of B I. In the denominator you have probability of A. Applying the theorem of total probability, we can write it as sigma probability of A given B j into probability of B j. J is equal to 1 to infinity. which proves the statement of the Bayes theorem. One thing which one can notice here is that the proofs of the statements of the theorems are quite simple. This is happening because we have given an axiomatic structure to the probability, and therefore, all the statements are simply consequences of certain relationships in the set theory. When the axiomatic definition was not known, all of these statements had complicated proofs, because if you use say relative frequency definition, then you have to look at the various relationships between the limits. If you use the classical definition, then you have to represent all the events in terms of favorable number of cases and the total number of cases, etc. So, all of these statements used to be quite complicated. The major contribution of the axiomatic foundation is that it made all the things extremely straightforward and also valid, because you can everybody can verify that the statements are true. As a let us look at the previous example of the IC defective problem. Suppose a randomly selected IC is found to be defective. What is the probability that it was supplied by say supplier B 1 or B 2 or B 3? Let us look at the first one. In the first one, we are interested in finding out the probability of B 1 given A. So, this is by the definition of Bayes theorem, it will become probability of A given B 1 into probability of B 1 divided by probability of A. We already evaluated the probability of A as 0.049. So, it becomes simply probability of A given B 1, that is 0.01 into 0.4, that is the probability of B 1 divided by 0.049, which is equal to 4 by so it is 0.004 by 0.049, which we can write as 4 by 49. If we look at probability of say B 2 given A, then in the same logic this will become equal to 15 by 49. If we calculate probability of say B 3 given A, then by the same logic it will become 30 by 49. You can see here the difference in the posterior probabilities. Although only 30% of the product comes from manufacturer third, but if the finally selected IC is found to be defective, then it is most likely to have come from the third supplier. The reason being that in the hypothesis of the problem, it has been assumed that more number of product from the third supplier are defective, which is actually 10%, whereas from the first supplier it is only 1%. So, although more supply comes from the first manufacturer, however, the probability that it came from him, provided it is defective, then the probability is much more small. So, this is an important you can say consequence of the Bayes theorem. B 2 given A is 15 by 49, probability of B 3 is 0.3, whereas probability of B 3 given A becomes 30 by 49, which is much higher. So, the probabilities get revised in the light of the knowledge about the outcome.